Welcome to the meadow census. As dusk settles, this quiet landscape comes alive with geese, deer, and foxes. Out here, the natural world is full of variables. We watch a deer approach a fork in the trail, or a bird search for a meal, and we face an immediate problem. How do we predict an unpredictable event? We don't know exactly which path the deer will take, or what color berry the bird will eat. We cannot predict the exact future. But what we can do is map out every single possible outcome. This animated diagram shows how those possibilities come together to form a probability model. In any probability model, the golden rule is that absolute certainty always equals the number 1. By dividing that solid 1 into smaller fractions, we can build uniform and non-uniform models. These models allow us to mathematically measure outcomes in the wild, whether they are equally likely or unequally likely. Let's build a non-uniform model. Imagine a bird finds a pile of berries on a mossy rock. A bag, or in this case, a rock, has 3 red berries and 2 blue berries. If each berry is equally likely to be picked, what probability model describes picking one berry? Our first step is to count total outcomes. 3 red plus 2 blue equals 5, establishing our denominator. Next, we assign the specific fractions to each outcome. Red has a probability of 3/5 and blue 2/5. Now for the crucial check. We sum the fractions. 3/5 plus 2/5 equals exactly 1. The math checks out. Answer: red 3/5, blue 2/5. Any valid probability model must list all the possible outcomes and assign probabilities that perfectly total 1. That rule holds firm, no matter how unequal the individual pieces are. Sometimes we need to test these theoretical models against reality. Take this flower wheel spinner, catching the meadow breeze. Our mathematical model predicts the wheel will land on red 1/4 of the time. Calculating the expected result for 80 spins, we multiply 1/4 by 80, giving 20 predicted red spins. But after 80 real-world spins, we observe red actually happens 26 times. Comparing observed data to our prediction, 26 is exactly 6 more than the 20 predicted. Our final answer is clear. The data produced more red results than the model predicted. The real world is messy. The wind blows, the wheel catches. Because of this, we use observed frequencies to judge how well a model fits. Probability models are incredibly useful guides, but they are not perfect crystal balls. Now let's look at a completely fair system. A deer arrives at a fork where the trail splits into 5 equal paths, labeled A, B, C, D, and E. What is the probability model for the deer choosing one path? As this geometric overlay highlights, our baseline state contains exactly 5 distinct paths. Because they are identical in width and distance, there are 5 equally likely outcomes. Because the outcomes are equally likely, the rule requires us to assign the exact same fraction of probability to each one. The math is verified. Answer: A, B, C, D, and E each have probability 1/5. When all outcomes hold equal weight, we use a uniform model. It perfectly and evenly fractures our total certainty of 1. Moving forward, every probability problem asks you to make one critical thinking move. You must look at a situation and ask, are these outcomes equally likely or not equally likely, and why? Whether you build a uniform model, like the 5 equal paths, or a non-uniform model, like the uneven red and blue berries, the architectural rules of probability are identical. This split-screen visual brings it all together. The mantra is constant. You must list the possible outcomes, assign their probabilities, and mathematically ensure they total exactly 1. Mastering this foundational rule of dividing certainty gives us the tools we need to decode even more complex, compound events hiding within the unpredictable wild.